What I want to do in this video is think about different ways to represent a molecule. And so we could start with, I guess you could say, the most fundamental way of representing anything, and that's with the name. And so let's say we're talking about the benzene molecule. Benzene. Well, a name's a start. You might point to a vial of something and say, hey, that right over there, that's a vial or that's a canister of benzene. But it still doesn't tell you much about, well, what's benzene actually made up of, and in what ratios do you have the different elements of benzene? To start answering that, you want a little bit more information. And the next step might be to have an empirical formula. So empirical formula. And I know what some of you might be thinking. What does empirical mean? And I thought that the first time I saw or heard the word. I think it might have been in, well, I forgot actually when the first time was. But it really just means through observation or through experiment. And so the early chemists, they didn't have super fancy electron microscopes and other techniques to look directly at a molecule of something. But they did have techniques, and we'll actually explore those techniques to figure out the ratios of the different elements that make up that substance. And they would have found that in benzene, for every carbon, there are actually two hydrogens. And actually, let me do the carbon and hydrogens in different color just for fun, so we can see them a little bit more clearly. So for every carbon, there's two hydrogens. Now, they didn't know, maybe each benzene molecule had more than one carbon. Maybe it had 10 carbons, and then if for every one of those 10 it had two hydrogens, it would have had 20 hydrogens. They didn't know. They just knew that the ratio for every carbon, you had two hydrogens if you had kind of a big bag of benzene. But as you can imagine, chemists and many people, including ourselves, we wouldn't be satisfied with just that. We would want to know, well, what are the actual number of carbon or hydrogen atoms that make up a benzene molecule? And to get that, we would then go to a molecular formula. A molecular formula. A molecular formula. We're not just giving the ratios, we're giving you the actual number of each atom in the molecule. So for example, the molecular formula for benzene, it turns out that there are 6 carbons in a benzene molecule. 6 carbons in a benzene molecule, and for every one of those 6 you have 2 hydrogens, so you're going to have 12 hydrogens. 12 hydrogens. So now you have more information. So you can always go from a molecular formula to an empirical formula. This right over here, this is easy to do. You're really just taking information away. You're just saying, okay, well look, for every 6 carbons I have 12 hydrogens, so for every carbon I'm going to have 2 hydrogens. You could just divide both of these by, I guess, their greatest common divisor. If you want to get mathematical about it, you could divide both of these by 6 and you'll get CH2, or you could say C1. You could even say C1H2 if you like. Now, this is somewhat satisfying. You now know, okay, in a benzene molecule, there are 6 carbon atoms and 12 hydrogen atoms. But it's probably not completely satisfying because you're thinking, well, how are these things actually arranged? What is bonding to what? And to get even more information, that's where a structural formula comes into play. So let me write that down. So structural formula. And I'll give you, I guess you could say, a fairly basic structural formula. As you advance in chemistry and organic chemistry, you'll have different variations for how people give a structure of a molecule. But a very basic structural formula for benzene would be something like this. So you're going to have 6 carbons. So actually let me do it in that same purple color that I've been using for the carbons. So you're going to have 1, 2, it's in a hexagon, 3, 4, 5, and then you have 6. You have a double bond between every other bond between the carbons is a double bond. And then each of these carbons are also bonded to a hydrogen. And as we advance in chemistry, we're going to talk more about what these bonds are. They're actually a sharing of electrons. So that right over there, actually I want to do in that same color. I want to be color consistent here. So that was actually more of an orangish color that I was using before. So hydrogen, 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 hydrogen. And we're done. This right over here is the structural formula. Notice this has the most, at least out of these three, has the most information. It's very easy to go from this to this, and then it's very easy to go from that to that. But going the other way, you'll need to learn things. You'll have to do an experiment or make some observations or kind of play around with some models to see how these things could fit together. So you're getting more and more and more information. As I mentioned, and this is only one variation of what a structural formula might look like. For example, when you go into organic chemistry class, a benzene ring will actually be represented just like this. And you might say, wait, how does this, what I'm drawing right now, have the same amount of information? Well, in an organic chemistry class, they just assume, hey, all of these vertices right over here, there are going to be carbon atoms, and if you don't see 4 bonds from a carbon atom, you just assume that it's bonded to a hydrogen. So in an organic chemistry class, you're just expected to know that, hey, that's a vertex, that's a carbon, 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 and each of those carbons are going to have 4 bonds. So if you're not showing 4, it's implicit that there's a hydrogen. That there's a hydrogen there. That there's a hydrogen there. So once again, that's another structural formula. Other structural formulas, they'll actually try to give you the 3-dimensional shape of a molecule. So once again, containing even more information. Now, the one thing I want to point out is that sometimes an empirical formula or molecular formula might be the exact same thing because the ratio is actually telling you how many of each element you have in the molecule. For example, if we were to take a look at water, what's the empirical formula for water? Well, for every hydrogen, or maybe I should say for every 2 hydrogens, you have 1 oxygen. That's actually the ratio of hydrogens to oxygens in water. Well, it also happens to be the case that each water molecule has exactly 2 hydrogens and 2 hydrogen atoms and 1 oxygen atom. So this is a case where the molecular formula and the empirical formula is the same. And this is a fairly simple molecule. If you have an understanding of how oxygen and hydrogen tend to bond, it's not difficult to come up with the structural formula, or at least a theory of what the structural formula should be. And we actually know what the structural formula of a water molecule it is. It is an oxygen atom, and it forms a single bond with each of these hydrogens. But anyway, the whole point of this is to just introduce you to the idea of these different ways to represent a molecule. And as we'll see, there's even different naming schemes for different molecules that are based on different conventions.